Thanks to Brilliant for sponsoring today's video.
Today we're going to look at a nice approach that defines Euler's constant E via differential equations. And I found this in a 2014 issue of Math magazine. Okay, so let's look at our setup here. So we're going to define this, new function that at the moment we don't really know much about called E of x as the unique solution to the following initial value problem. So we have y prime equals y and y of 0 equals 1. So since e of x satisfies this initial value problem, that means the derivative of e of x is itself, and e of 0 is equal to 1. And I guess we're using some theorems from differential equations to know that, well, there is a unique solution to this initial value problem. Okay, so let's start with an observation that we're just going to outline the idea of the proof, but it'll be important as we move forward. And that is, for all real numbers x, e of x is bigger than 0. So in other words, the solution to this initial value theorem problem, or this initial value problem, is always positive. And well, how does the proof go? Well, one proof at least goes like this. So if we've got a place where it's less than 0, then by the intermediate value theorem, there's got to be a place where it equals 0, because the solution is going to be continuous. And if it's negative somewhere and positive somewhere else, then that means somewhere in between it must pass through the x-axis. Now, if it's never negative, but it's equal to 0 somewhere, well, then we can really cut out this step. And then what we'll do is take the 0 of the function and do a Taylor series expansion of the function at that 0. But since the function is always equal to its derivative, that means all derivatives are equal to 0 there as well. And then, well, that means that the Taylor series is identically 0 expanded around that point. But then you can also check that that has an infinite radius of convergence, meaning that the function is identically 0. Oh, but we know that the function must be equal to 1 at 0, so that's a contradiction, meaning that yes, our function is positive.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing. And that's why I highly recommend you sharpen your skills with Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. Brilliant is a unique learning platform that matches you with the right content for your current skill levels, then improves upon this with fun, hands-on lessons that are proven to help you learn. Content is designed by award-winning teams from MIT, Caltech, Duke, Microsoft, Google, and more. Their new data content is perfect for people of any level and can help you learn data analysis. They have a fully built-out suite of new content, from Bayes' theorem to multiple linear regression. But we're scientists here, so don't take my word for it. You should go test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/MichaelPenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So now that we've gotten that taken care of, what's our real goal here? Well, our goal is to show that e of x is equal to e to the x, where by e we mean e evaluated at 1, and we'll show that that is the familiar constant. And well, there are a couple of ways to define this familiar constant, but we're going to look at its definition via a certain limit. But that's near the end of the video. Okay, so let's start with the following claim, and this is the multiplicative additive maybe rule for exponential type functions. E to the a plus b is e to the a times e to the b for all real numbers a and b. Okay, so how might this go? Well, let's set a new function f of x equal to e to the x plus b minus e to the x times e to the b. And well, let's notice that f prime of x is equal to e to the x plus b minus e to the x times e to the b. Well, that's by the chain rule for the first term. Our composed function has a derivative of 1. And well, that's by the constant multiple rule for the second bit. But observe that that's the original function. So we have f prime is equal to f of x. So that's perhaps the first thing that we need to notice. And the second thing is if we evaluate f at 0, we'll get e of b minus e of 0 times e of b. But e of 0 is equal to 1. So this is e of b minus e of b, which is equal to 0. Okay, so what does that tell us? Well, we've got our function f of x satisfies a certain initial value problem. And that certain initial value problem is y prime equals y and y of 0 is equal to 0. But let's notice that a very, very simple function also satisfies this initial value problem. So observe that it's also satisfied by the function, which I guess we'll call g of x, although we don't really need to call it anything. It's simply the 0 function. But then by the uniqueness of solutions to initial value problems, we know that f and g must be the same. In other words, we know that f of x must be identically equal to the 0 function because g of x is the 0 function. But then look at this. If f of x is identically the 0 function, then moving some things around, we get the identity that we're looking for. Okay, so there we have it. We've proved this multiplicative additive identity, and now let's move on to some other identities. Okay, so we just finished proving this multiplicative additive identity for our function e of x, and now, well, let's see where this takes us. So it immediately takes us to the following place. So let's notice for all natural numbers, and I'll call them m, we have what? Well, we have e of x to the m power is simply e of x multiplied to itself m times. But then we can apply this rule over and over and over again to turn this into e of x added to itself m times, where now the addition is happening within the function. But you know, that's pretty clearly equal to e to the m times x. By the, well, that's simply the definition of multiplication, and the definition of exponentiation took us from one place to the other, along with, well, our original claim. Okay, well, now how might this help us? Well, let's notice if we have x equal to 1, then we have this nice identity here, and that is e to the m. Well, that's going to be equal to e evaluated at 1 to the m, because that's how we're defining e at the moment, as e evaluated at 1. But then that's going to be e evaluated at m. But then let's also notice that if we set x equal to 1 over n, then, well, what do we have in this case? Well, we have the following. E evaluated at 1 over n to the m is now going to be equal to e to the m over n. And, well, this last identity is actually, well, not just this last identity. These two little special cases will be important for the following maybe equation, and that goes like this. Let's look at e to the m over n raised to the n power. Now, by exponent rules, that's simply equal to e to the m. But then by this first line right here, that's going to be equal to e evaluated at m. But then we can write this as e times n, or E evaluated at n times m over n. But now, well, that's simply going to be E evaluated at m over n raised to the n power. So now let's zoom out a little bit and observe that we have this E to the m over n raised to the n power is equal to E evaluated at m over n raised to the n power. Now, you might say, well, that doesn't guarantee equality of those two magenta underlined things, but it does in the case that they're positive, which they are positive. So since they're positive, like I said, those two magenta underlined things are equal, and we have E to the m over n is equal to E evaluated at m over n. But what does this mean? Well, this means that our function is equal to, well, this exponential function for all rational numbers, because all rational numbers can be expressed as m over n, for appropriate integers m and n. Okay, but then since we know that the rational numbers are dense in the real numbers, and our function must be, well, smooth and so forth, because it satisfies this nice setup right here. What that tells us is that e to the x must be equal to E evaluated at x for all real numbers x. Okay, well, that's good. So I think we've achieved part of our goal here. We've shown that E evaluated at x is E to the x, where E is equal to E evaluated at 1. You might say, well, that's our whole goal, but we need to finish it off with is the familiar constant, which, like I said before, we're going to use the definition for this familiar constant, Euler's number, a very famous limit. Okay, so let's dive into that. Okay, everyone, so we're going to now show that our function E, which we are defining to be E evaluated at 1, where our E of x function, well, we've been talking about the whole time, is in fact equal to this very, very famous limit. So the limit as n goes to infinity of 1 plus 1 over n to the n power. Now, maybe the way that most people have seen to evaluate this limit inside of a calculus class is observe that it's a certain type of exponential indeterminate form, which can be evaluated using logarithms. But that uses, quite a bit of machinery, which we haven't developed yet, via our very, very simplistic definition of this number E. So we're going to do it without that. But maybe before we do that, I'd like to point out that another way of defining E is pretty easy to get to via our, current interpretation of the number, and that is as the sum as n goes from 0 to infinity of 1 over n factorial. And well, that's because the Maclaurin series of our function E of x is built very, very easily given that all derivatives of E of x are equal to E of x, which means that all derivatives evaluated at 0 are equal to 1. And then essentially it just falls apart immediately. So let's focus on this limit definition of E. Okay, so now we're going to start with the mean value theorem. So, well, anytime you're talking about the mean value theorem, we need to talk about which function we're using it with, which is our E of x function. And then, well, what interval? So the interval here, the function is E of x, with the interval being the interval from 0 to 1 over n. So the 1 over n part probably shouldn't be much of a surprise given that we've got 1 over n's baked into our limit right here. Okay, so what does that tell us we're able to do? That means that we can find a number c on the open interval from 0 to 1 over n, where the average rate of change on that interval is equal to the instantaneous rate of change. In other words, E prime of c is equal to e of 1 over n minus e of 0 over, well, nominally 1 over n minus 0, but that's simply 1 over n. But then since the derivative is equal to the function, well, we can just extend that off the left to have e prime of c is equal to c. Okay, but then let's also note that e of x is increasing. Now, you might say, well, how do we know that? Well, from this over here, we know that e of x is always positive. But since e of x is equal to its derivative, that means the derivative is always positive. But the derivative being always positive means that it is increasing. But what does that tell us? Well, since c is between 0 and 1 over n, we have e of 0, which is equal to 1, so let's put that at the left, is less than e of c, which in turn is less than e of 1 over n. And now from here, what we're going to do is exploit both halves of this inequality. And I'm going to color code them. So the first half is going to be color coded with this green underline bracket. And observe that we're going to have 1 is less than e of c. But we know that e of c by the mean value theorem is equal to that stuff right there. That's how we in fact chose c. So we know that this is going to be less than e of 1 over n minus e of 0, which we know is 1, over 1 over n. But then from there, it's pretty easy to move some things around, and we'll have 1 over n plus 1. Maybe I'll write that as 1 plus 1 over n is less than e to the 1 over n. Okay, so that's a nice place to be at the moment. And now, well, we're going to exploit the other half of that inequality. And by the other half, I mean this bit right here. E of c is less than 1 over n. And let's do our, well, like I said before, our color coding. So we've got blue for that. Now let's replace e of c with what we replaced before. So we have e of 1 over n minus 1 over n is less than e of 1 over n. Now, again, we can move some things around here, and we'll do this in a couple of steps. That gives us e of 1 over n minus 1 is less than 1 over n times e of 1 over n. We can solve for e of 1 over n, if you will. And what we'll have is, well, not solve for e of 1 over n, but maybe isolate the e of 1 over n terms. And we'll have something like this. We'll have 1 minus 1 over n times e evaluated at 1 over n is less than 1. Okay, so I think that's looking pretty good. And from here, what we'd like to do is introduce a 1 over n plus 1, or a 1 plus 1 over n term. So we'll do that by taking this entire inequality and multiply by 1 plus 1 over n. And we're doing that to make the right-hand side of the inequality look like the left-hand side of our, well, existing inequality. So that's going to give us 1 minus 1 over n squared times e to the 1 over n, which of course I'm doing by multiplying that out, is less than, well, 1 plus 1 over n. Okay, so that's pretty good. And now, well, let's take a look at this, and we'll start the next board by gluing these two inequalities together. So we've got these two inequalities that I'm underlining in purple, and observe that they both have this 1 plus 1 over n term. Okay, so like I said, let's start the next board with that. Okay, so now we've got those two inequalities that we built on the last board glued together. But let's look at our limit and observe that we've got an exponent of n here. Well, what does that mean? Well, that means we should probably exponentiate all parts of this limit to the nth power. So let's do that. So I'm going to put an n here in the exponent. This is going to be raised to the n. Here I'm going to put an n here in the exponent, and then this e to the 1 over n. Well, that's also going to be exponentiated to the n power. And then, well, let's observe over here from one of our very, very original claims. we know that e to the 1 over n raised to the n is equal to e evaluated at 1, which is simply equal to e by our definition. Okay, so let's bring that down. So we'll have 1 minus 1 over n squared times e is less than 1 plus 1 over n raised to the n, which in turn is less than e. So let's observe that the right-hand side of that is good to go. Of course, if we're going to use the squeeze theorem, which is what we're setting up here, I forgot my nth power here. But what about that left-hand side? Well, that's still an indeterminate form, but there's actually a classic limit that will allow us to push something to the left of this. So let's perhaps recall this classic. I said limit, but I meant inequality. So here, I'll just call this classic for classic inequality. And that is that 1 minus x raised to the k power is in fact bigger than 1 minus k times x. And well, I mean, there are some rules about x, but maybe as a nice exercise for yourself, you can look at what values of x this works with and observe that we're in that setup here. Of course, here, our k is played by n and our x is played by 1 over n squared. So pushing that this way, we'll have what? Well, we're going to have 1 minus 1 over n times e with a distinct lack of exponentiation by n. But now we can apply a limit to the extreme left as well as right-hand side of this inequality. So, and that inequality, or that limit, will be as n approaches infinity. Well, sort of obviously, as n approaches infinity to the right, we get e because there's no dependence on n. As n approaches infinity on the left, we get 1 minus, oh, well, that's simply going to disappear. And so we're going to get e here as well. But let's look at what's sandwiched in the middle here. And what's sandwiched in the middle here is exactly what we want up here. And, well, then by the squeeze theorem, we have proven this claim. And, well, of course, we didn't really do anything new, but it's always good to look at things from different angles. You learn a lot by doing that. So maybe post in the comments if you have another of your favorite creative approaches to familiar mathematical constants. And that's a good place to stop.